Hello everyone, I'm Raymond from LinkedIn and I'll be talking to you about auto sizing for stream processing applications. This is joint work with Bharat, Pratik, and Sam. So stream processing applications are those that cater to use cases where you have input data in the form of streams. For example, if you have a stream of job listings on LinkedIn and a stream of candidate skills and you want to match jobs to candidates and compute the top skills that are finding jobs in a real-time fashion or a near real-time fashion. And there are a number of systems today that you can use for these apps, for example, Apache Flink, Storm, Samza, Heron, Spark Streaming, and so on. Other examples of stream processing apps include apps that send email digits and notifications, apps that monitor service to service calls, apps that help conduct and analyze A B test results in a real time fashion. At LinkedIn, we run thousands of such apps which fall into different logical categories, processing millions of messages per second, translating to hundreds of gigabytes of data per second. And the way stream processing works for us is by providing it as a service. What that means is we provide SDKs and APIs for users, which are typically app developers or data scientists, that they use to write their logic, while the service bears the onus of maintaining and managing the app in terms of capacity provisioning, operational issues, security of the apps, and the standard desirable of scalability, efficiency, fault tolerance, performance, and so on. But the problem is users are left with the challenge of sizing their apps in terms of the amount of memory, CPU, tuning things like the number of threads, memory allocation in terms of heap versus native, or enabling specialized hardware for their apps. And it is hard for users to make these sizing and tuning decisions. Consequently, what happens is users either vastly over-provision the amount of resources which leads to waste. For example, in our experience, half the users over-provision by at least 50%. A recent paper from Google on a similar topic had also had similar findings. Or what happens is users under provision, which leads to their apps running out of memory, stalling, failing, oftentimes underperforming, and causing operational issues. So what we want, therefore, is a controller that takes as input an app's latency and throughput goals, its input load, details about its internal, like its service dependencies, details about the network latency or environmental conditions in general, and tunes and sizes the application's parameters. And if you look at existing work on building such controllers, they can kind of broadly be categorized into two categories. First, we have work that relies on apps being a DAG of well-known cataloged operators like a map, a join, filter, and so on, with predictable performance and resource characteristics. And this work then focuses on tuning parallelism for different stages of the apps to optimize for throughput, latency, resource utilization, time taken for tuning itself, and so on. And the second category of work relies on certain assumptions about the input load or per message service time of the apps and combines that with algorithmic approaches to similarly tune parallelism for different goals. So what we did is we compared these approaches with actual production applications to see if the assumptions they make are valid, what problems we would face if we were to apply these approaches in production, and what insights can we draw, which then would pose as challenges that a controller should address. So the first thing we notice is a large fraction of apps leverage remote services for processing input. These are in the form of blob or key value store, web services for controlling content, notifying users, and so on. And what that means, therefore, is that apps' service time directly depends on these services' latencies, failure rates, and network latencies, and so on. And unlike assumptions in existing work, this follows no specific distribution. It could be a long tail or multimodal, and so on. Similarly, such applications' throughput also depends on the remote services throughput in addition to the input load. And input load by itself can also vary with time, and arrival rates therefore don't follow any specific distribution. The second thing we observe is that apps go much beyond than being a directed acyclic graph of operators or a DAG of operators, which significantly changes their resource requirements. Apps load and use external resource-intensive frameworks like DL4j or TensorFlow. Applications may use user-defined functions or UDFs for different parts of their processing logic. Apps may maintain local persistent state using stores like RocksDB, and that state may be replicated to remote stores. Apps may also tweak processing semantics, for example, enable out-of-order processing, customize data consumption behavior, and so on. And what we see is that different apps combine functionalities in different ways. So here is a heat map that measures the overlap of different functionalities that production applications use, which leads us to believe that DAG-only models, although useful, are insufficient for sizing because of this wide spectrum of functionalities and their combinations that apps use. Another thing we observe about apps is that they exhibit correlations in their use of resources. For example, an application that is undersized on CPU or bottlenecked on CPU and is therefore straggling can show increased service time, leading to increased buffering of the input, therefore increased memory use in addition to lower throughput. Similarly, in case of Java-based systems like SAMS and Flink, an application undersized on memory can have frequent garbage collection runs, which can cause latency to rise, CPU use to spike, and throughput to drop. And this is something we found was largely ignored in existing work. And lastly, looking at the range of applications as a whole, we see that applications differ significantly in a number of characteristics, which means the controller cannot rely on specific design or implementation assumptions such as thresholds about them. For example, the average service time for an app may range anywhere from 10 microseconds per message on an average to 10 seconds or more. Similarly, the number of input streams of an application could range from one or two to thousands of them. The amount of local state that an app maintains could also range from a few kilobytes to terabytes. So what we want, therefore, is a controller to address these challenges and in doing so meet a set of requirements. First, the controller should be able to right-size the application, that is, compute a resource sizing that even though may not be the optimal size, but bounds over provisioning while preventing under-provisioning and all the consequences of under-provisioning at all times. Similarly, it should allow service providers to manually to manually override or tweak the decisions or sizing decisions if required, understand the sizing decisions, but more importantly, in going to the right size for an application, starting from a size, the controller should follow a trajectory that does not increase undersizing related issues. The controller should, of course, minimize the amount of time taken to go to the size, should scale to a large number of apps, be fault tolerant, resource efficient, and so on. So how do we go about building a controller that meets our challenges and requirements? One option is to take a black box strategy, where the controller applies a decision on an app, then relies on refining or undo or redoing that action. This is similar to how rule-based auto-sizing, auto-scaling works for Azure VM scale sets or AWS EC2, where a user defines independent rules for each resource. This approach is although simple, understandable, and produces right size, but it does not account for an application's internals, such as an application's CPU and memory use being coupled. It has been shown to exhibit oscillations, that is, the controller never converges or takes a long time to converge, neither of which are very desirable in production. But then an alternate approach is to model the effect of each resource parameter on each application and formulate sizing as an optimization problem. This relies on profiling apps using trial runs or making assumptions about the optimization function and then tuning the model parameters. So with this, you can minimize the time taken to get to the optimal size, but it lacks the understandability and ease of modifying behavior at runtime, for example, for handling operational issues, say due to a faulty remote service that an app talks to or increased network latencies. So what do we do? What we do here is we take an approach that is sort of midway between the two and design a new controller or a new control system called Sage. Sage is simply a feedback-based control system but incorporates strategies for sizing resources into policies. Each policy is responsible for sizing a single resource, and policies are organized in a priority order. A policy is applied on an application only if no higher order or higher priority policy has yielded an action to change size for a given job or a given application. In addition to ease understandability for apps in production, Sage serializes the policies applied on a given app, which means it serially changes the resource sizing for different resources. Having a priority order like this, like the one shown here, has two key benefits. First, it allows a deterministic order of sizing of applications resources, regardless of the type of applications, the functionality that the app uses, and the other degrees of freedom that we talked about earlier. The second benefit of this approach is that it allows for easy programmability of the policies themselves. What that means is that given a policy, A given policy can therefore assume that resources corresponding to policies higher up in the priority order do not need any tuning or adjustment. For example, say a policy is responsible for sizing an application's degree of parallelism in terms of number of threads or number of processes. So such a policy can then assume that the application currently has no memory or CPU bottleneck because this policy is lower down in the priority order than the CPU and memory policies. So this makes writing and tuning such a policy much, much easier. And given this, what we have done is we've tailored the priority order to what are called continuous operator systems like SAMS and Flink. Other types of systems will likely need to tweak the policies in the priority order. Our paper has more details about this, but let me try and explain this with a sample scenario. So say an application is straggling and not keeping up with input load. Now this could be due to a number of bottlenecks, memory, CPU, parallelism, and so on. So however, in continuous operator systems like Flink and SAMSA, buffers used for input buffering are bounded on size, while other systems could be dynamic based on memory availability. So what this means is that by tuning memory alone, one can guarantee that an app has a stable, non-failing operation. It may have high service time because of a CPU bottleneck or poor throughput due to a parallelism bottleneck and so on, but those are then acted upon by subsequent policies. Similarly, policy tuning parallelism can measure the application's backlog increase rates and correlate that increase or correlate that backlog increase with metrics of any remote service that the app uses. And then based on that, accordingly, can scale up the parallelism of the app. I won't be covering the scale down part of things here, so please refer to our paper for that. And we've implemented Sage as a stream processing application itself, since it processes streams of incoming data from other applications. It's approximately 6,000 lines of code, and we've enabled it on hundreds of production applications. In production, on average, Sage takes about 30 minutes to right size an application from start, and its right size is approximately 14% larger than a hand-tuned optimal size. Now, even though 30 minutes seems like a lot, it is largely because in production we want to control the reactivity of the different policies. And lastly, Sage scales down resources by applying a single safe scale down action for each resource like CPU and memory, which we detail again in our paper. So to conclude, resource sizing is crucial for any service's performance, usability, operability, especially when it comes to stream processing apps since they constantly operate under variable load. However, what we find is that production apps today go much beyond their conventional view of being a DAG of operators. They leverage remote services, have heterogeneous functionalities, combine functionalities in different ways, and have widely varying workloads that don't necessarily conform to distributions assumed in literature. So therefore, resource sizing for such apps involves navigating the complex trade-offs between resource utilization, performance, cost, and operability. What we've done here is built a rule-based system called Sage that handles these trade-offs and is tailored to our production applications.